Hello everyone. In this video, I will go over my solution for the problem named binary strings are fun, taken from today's Codeforces round. This problem is an excellent combinatorics problem, which will teach you how to find and count the number of good extensions of a binary string for each and every subarray of the binary string. So it's one thing to find the number of good extensions for the entire string, but we need to find the number of good extensions for all possible subarrays of the string, which makes it harder for us to count. And I'll be explaining how we can use some combinatorics principles in order to find this number. So a binary string of odd length is good if the ith element for all odd indices I is the median of the first I elements in the string, and the median is basically defined as the element which appears at least n times. So if 0 appears n times, at least n times in this odd length string, then 0 is the median. Otherwise, we know that 1 will appear more times. That is why 1 is the median for the odd length string. We are only considering odd length strings because we know that for even length strings, there could be the case that both zeros and ones appear equal number of times, in which case there is no fixed median, but we are only worried about odd length strings. So this is the median for the odd length strings, and we want to find out the number of good extensions. So an extension of a string is basically a string of odd length given an initial string of length n. You construct another string of length 2n minus 1 by basically adding n minus 1 places in between. So let's say you had initially n places, 1, 2, 3, let's say n is 5 for example. So let's say you had 5 places, 1, 2, 3, 4, 5, or 0, 1, 2, 3, 4, whichever way you want to call it, and you add 4 places in between. So you add these 4 places in between. So the new string will have a length 2n minus 1. So there are initially n places, and you add n minus 1 places to get a string of length 2n minus 1. So this is called an extension, where you insert one character in each of these places. And it's important to understand that an extension basically means that these characters remain fixed. So these characters are fixed, and you can put anything you want in these characters over here in these places. So that's why it's clear that there are 2 raised to n minus 1 possibilities for what all can be put in these n minus 1 blanks, because each blank can have either a 0 or a 1. However, the number of good extensions are only those extensions which satisfy this condition that bi is the median of b of 1 to I. So this basically means that the first element should be the median, which is obviously satisfied. Third element should be the median, which may not be satisfied, uh, but we'll consider cases in which it is satisfied and which it's not satisfied. Similarly, the fifth element should be the median of the first 5 elements. The seventh element should be the median of the first 7 elements, and the ninth element should be the median of the first 9 elements, and so on. So we need to ensure that this happens for this extension to be good, and we want to find out how many such good extensions are there and print that value. So first, let's try to find out the number of good extensions for the entire string, and then I'll explain how we can extend that for all substrings. So in the first example, if we have the string 0, 0, 1, then it's clear that we start off with placing 0 over here. There's a gap, then there's a 0, then there's a gap, and there's a 1. And we want to find out how many possibilities are there. So first of all, 0 should be the median for the first 3 elements. So this means that this can be either a 0 or it can be a 1. So this is another possibility, either a 0 or a 1. In the first case, since we want 1 to be the median of the entire string, we'll have to put a 1 here. However, it's still not satisfied that 1 appears the majority number of times. That is why this doesn't work. And there's only one possibility in which in which we put a 1 over here, because again if you put a 0 over here, 1 appears only 2 times, 0 appears 3 times, but we want 1 to appear at least 3 times. So this is why we must ensure that 1 appears here, and in this way we can see that there's only one possible string, one possible good extension for the entire string. Now let's consider another example. So let's say it was when it's 0 0 1, we know that the answer is just 1. When it's 0 1 1, when it's 0 1 1, then let's try to figure out the answer, and let's see if there's some pattern. So when it's 0 1 1, we'll again do the same method of putting the blanks and putting the ones and zeros, and we know that since 1 has to be the median, there's only one possibility, which is to put the 1 there. And over here there are two possibilities. You can either put a 0 or you can put a 1. Both these possibilities work, because if you put a 0, you'll still get the median as 1, because 1 appears 3 times. And if you put a 1, you'll still get the median as 1, because 1 appears 4 times now. So that's why there are two possibilities for this case, when it's 0 1 1. And when it's 1 1 1, then actually all possibilities are valid, because if you put a 1, there's a gap, there's a 1, there's a gap, and there's a 1. This means that there are two possibilities here, two possibilities here, for a total of 4 possibilities. So all 4 possibilities are valid. And if you extend this idea for larger strings, so if you extend this for, let's say, 4 ones together, you will notice that there's going to be 8 possibilities, because all possible gaps can be filled in any manner. So all possibilities for filling the gaps are valid. And in general, when there are n ones together, there are going to be 2 raised to n minus 1 possibilities. So 2 raised to n minus 1 ways in which you can fill the gaps. And over here, n basically represents the longest suffix of continuous elements. So longest equal element suffix. And basically what I'm saying is that if you consider the suffix of equal elements, so there's a suffix of one element which is equal, which means that 2 raised to 1 minus 1 is 2 raised to 0, which is 1. If there's a suffix of 2 equal elements, then it's 2 raised to 2 minus 1, which is equal to 2 raised to 1. If there's a suffix of 3 equal elements, then it's basically 2 raised to 3 minus 1. And in general, if there's a suffix of n equal elements, then there's going to be 2 raised to n minus 1 ways, because any possibility for filling the last n minus 1 gaps is acceptable. So n basically represents the longest equal element suffix, and you can verify that this is actually going to be the number of ways for any complete string. So if you take another example, let's say you take this entire string, then because there's a 0 in the end and there's only one 0 in the end, there's going to be exactly one good extension for this entire string, because 2 raised to 1 minus 1 is 1. So 2 raised to 1 minus 1 is 2 raised to 0, which is 1. And because there's a 0 over here, you're forced to fill everything else with zeros. And that's why there's only one way. If there were 2 zeros, then you had 2 raised to 1 possibilities, because you could choose where to put the ones as well. And if you had n consecutive zeros, it would be 2 raised to n minus 1 ways in which you could fill the n minus 1 spaces. And I hope you understood why intuitively figuring out the longest continuous suffix, the longest consecutive suffix, in which all the elements in the end are equal, and basically raising 2 raised to that suffix minus 1 gives you the number of ways for the entire string. And now what we basically need to do is figure out how many elements are there, how many such extensions are there for each substring. So we found out for the entire string it's 2 raised to suffix minus 1. So let's call the suffix s. So it's 2 raised to s minus 1 ways, where s is longest suffix, where longest equal elements suffix. So longest suffix with all longest equal length suffix, or longest suffix with all elements equal. This is what s represents. And we know that there are going to be 2 raised to s minus 1 ways. And this is for the entire string, But for some substring, we can use the same idea. So for any substring L to R, we can find out what is the longest suffix which ends at R and goes possibly up till L. And it's going to be 2 raised to s minus 1 for every substring as well. So this means that we want to find out the sum of 2 raised to s minus 1 for every substring L comma R. Now let's try to find out a way in which we can do this efficiently without having to actually iterate through every substring. So the key idea for computing the sum of the number of good extensions for every substring is to compute it for every substring ending at I, for all I going from 1 to n. So we'll just keep adding this to a variable called sum. So initially sum is 0, and for each I going from 1 to n, we calculate the number of good extensions ending at I. So to find the number of good extensions ending at I, we will basically try to find out how many good extensions. So sum is 0 and sum plus equals to number of good extensions ending at I. So I is the right endpoint of the string, and we know that the left endpoint of the substring will be sum L and the right endpoint will be I. Now if I minus L plus 1, which is the length of the string, is greater than or equal to the suffix, the longest suffix s, which ends at I, then we know that the answer will just be 2 raised to s minus 1. So the sum will increase, the number of good extensions will increase by 2 raised to I minus 1. Otherwise, the number of good extensions will basically increase by 2 raised to I minus L plus 1, because this entire string will be a suffix of equal elements, because if s was less than or equal to I minus L plus 1, then we consider only s, otherwise we consider the entire string. And if you rephrase this, and if you want to write it in a better way, you'll notice that we basically just need to consider, so first we can find out the value of s. So find s in the following manner. To find s, by initializing s to 0, by initializing s to 0 and increasing s by 1 if string of I is equal to string of I minus 1, otherwise resetting s to 0. So if string of I is equal to string of I minus 1, we increase s by 1. Otherwise, so if string of I is equal to string of I minus 1, we do s plus plus. Otherwise, we reset s to 0. And now we basically need to add up the sums of powers of 2 of s. Notice that by setting s to be equal to 0, I'm essentially subtracting 1 directly. It should be s is equal to 1, and then we do s minus 1, but I'm starting with s is 0. So that's why you don't need to subtract s. You don't need to subtract 1 from s when you're adding 2 raised to s. So this basically means that the sum of all number of good extensions ending at string I, ending at position I, will be 2 raised to s plus, so it will start from 2 raised to 0, then it will go to 2 raised to 1, then it will go to 2 raised to 2, all the way up till 2 raised to s plus 2 raised to s plus 2 raised to s plus 2 raised to s a number of times. And the key idea is that this will be for the first s plus 1 left endpoints, and this will be for the remaining left endpoints, because we know that the right endpoints, we know that the right endpoint is fixed at I, and that's why the left endpoint can be anything from I minus 1 till 1 till 0. So this is when the left endpoint is equal to I minus 1. This is when the left endpoint, so this is when the left endpoint is equal to I. This is when the left endpoint is equal to I minus 1. This is when the left endpoint is equal to I minus 2, and so on, all the way up till the left endpoint is equal to s minus I plus 1, I think, and so on, all the way up till the left endpoint is equal to 0 or 1, whether you're using 1-based indexing or 0-based indexing. And then in order to find out this entire sum, we'll use the fact that 2 raised to 0 plus 2 raised to 1 plus all the way up till 2 raised to s minus 1 is equal to 2 raised to s minus 1. So this is a useful property for finding sums of powers of 2. And we need to multiply 2 raised to s. We need to multiply 2 raised to s. L minus s minus 1 times, I think. You can just rearrange this to get I, and you will see that the expression is this. So I is equal to s minus L minus 1, or basically I minus L. So I minus s minus 1 will be the number of times, the number of remaining left endpoints when when you need to get the number of good extensions. So this should actually be I minus s plus 1, and L should be actually equal to I minus s plus 1, because we know that for the first s left endpoints, we are going from 0 till s minus 1, and then the s endpoint will be this, and then the s plus 1th endpoint will be this, s plus 2th endpoint will be this, all the way up till the starting left endpoint. And that's why if you work out a few examples, you'll see that we are getting the term 2 raised to s exactly I minus s plus 1 times, and all the remaining times we are getting 2 raised to 0, 2 raised to 1, all the way up till 2 raised to s minus 1. So if you add up all these, you'll get 2 raised to s minus 1 plus 2 raised to s into I minus s plus 1. You can simplify this further, but it's not required. And this math reduction may seem a bit tricky, which is why you should try to do it yourself on paper and look at this part again. So basically what I'm doing is I'm trying to find out an O of 1 expression for every substring. We know that the O of 1 expression for every substring is 2 raised to the suffix minus 1. We can maintain the suffix iteratively by going for each I from 1 to n minus 1, and we can find out the contribution for the ith value by basically summing up 2 raised to 0, 2 raised to 1, all the way up till 2 raised to s, and 2 raised to s a number of times. And to figure out those numbers, you should try out a few examples, and you'll see that I minus s plus 1 is the number of times 2 raised to s is being contributed, and the remaining times 2 raised to 0 all the way up till 2 raised to s minus 1 is being contributed. 2 raised to 0 is being contributed for I comma I, 2 raised to 1 is being contributed for I minus 1 to I, and all the way up till 2 raised to s minus 1 is being contributed for the substring L comma I, such that I minus L plus 1 is equal to s. And that's why for all the remaining elements from 1 till L or from 0 till L, you'll get all those elements should have a suffix of length 2 raised to s. So there are these many number of such left endpoints. So you'll add the contribution of 2 raised to s for each of those left endpoints, and you'll get this expression. So now I'll show you the code which implements the same idea. So in the code, I use ll mod, and it's a constant modulus which is defined in the problem statement because we are calculating powers of 2, which can be very large. So that's why you use modulus this number. And for each test case, I take in the string s. I calculate powers of 2. So p of I is equal to 2 raised to I under mod. So I use percentage for mod. And for each I going from 0 till n minus 1, if I is 0 or string of I is not equal to string of I minus 1, we set the suffix to be equal to 0. So s is actually 1, but we are calculating sums of powers of 2 raised to s minus 1, which is why I initialize s to be 0 and increment s whenever string of I is equal to string of I minus 1. And in the end, we know that there are total of I terms from 0 till 1, 2, all the way up till s. So that's why I minus s plus 1 terms of p of s will be there. So we multiply p of s into I minus s plus 1. So this is basically 2 raised to s. And the remaining terms are 2 raised to 0 plus 2 raised to 1 all the way up till 2 raised to s minus 1, which is basically 2 raised to s minus 1. And we add that to the sum, and we take some modulus, and we print sum with a backslash n because I'm using fast IO. So you can verify that this code gets accepted. So I hope you like this problem and my solution. If you have any doubts in any part of the solution, do leave them in the comments down below. And if you like this video, don't forget to give it a thumbs up. Thank you.